We're going to start with talk about relays, and I want to show you a picture of relays before we do anything else. So this is what a relay looks like. Okay. Now, inside a relay, there's contacts that close and open, and this is the coil, and these are the contacts. So when you energize from here to here, these pull in and these open. Normally closed open, and normally open closed. Now, there's all different types. One is called a double pull, double throw relay. One's called a Form C relay. And there's also a Form C double pull, double throw relay. So you have all different kinds of relays in this pictorial right here, okay? That's my fingers there that you can see. And this is one of the ones we're going to pass around today. But that's the picture of a relay and the coil of a relay. And when you energize a coil, it moves these contacts from the fixed side. This thing moves. It physically moves, and that's how you change the state of it. Okay. Now, also in this, there is the idea of building up of circuits, and you can do that as well. And we talk about that in chapter 2 of this book, and we talk about how you can build circuits with that's not a capacitor, that is a relay contact. Okay, it'd be a normally open contact. It's a normally closed contact, and I want to pass some of these around, and that's the coil of a coil of a relay right there. All right, so when you push a button, this is going to energize, and when that energizes, this is going to close, and this is going to open. So if you push the button, this light turns on and this light turns off. Okay. And then you can also build and OR circuits with these. And there's a relay again moving and all that kind of stuff. And there's a picture of another one of the relays. This is one that's going to be passed around together. And that is the picture of the coil. And it looks like an O, and that's why the circle is on the screen like it is. This is another type of contactor. There's a push button. And there's a big push button, and there's a timer. But here are some pictures of how you can build up circuits. This would be an AND circuit. This would be an OR circuit. And then we get down into, skip this part, and actually building a relay circuit, okay? And that's a motor starter. We're going to skip that. We're going to come down here to an actual circuit that we can actually build. And you say, what are you going to do about this? Well, we're going to build some circuits like this in this course a little bit later. But I want you to understand some of these concepts. Now, this is a little bitty relay. This is a Form C contact, and this is the coil. And if you touch 12 volts from here to here, it turns on, and you can actually see this. And this is one that I'm going to pass around for you inside. Actually, cut it away, and you can actually see this is. You're going to get to see this one. And this is the relay that you'll probably use in your project at the end of the course. These are Form C relays, but they're 24-volt relays, and I'm going to pass these around as well. I'm going to show you these today. And then you can build circuits with these. And here is that circuit. There is our push button, and there's our control relay, there's our CR, there's our coil. And when this energizes from here to here, energizes, passes current through, this turns on. In other words, this passes power. That light turns on, that light turns off. So you're going to build this, you're not going to build that circuit, you're going to build another one, but I'll show you what you're actually going to build. And this is how you would use the terminals. Okay. Again, get used to it because you're going to be building this. So we switch in this course from just using circuits that you would have for like L's, R's, and C's to digital logic. In this course, you're going to see a little bit of both. And this would be an AND circuit. This would be the person here pushes this button and the person here pushes this button. Here would be an AND circuit. This would be the button push for number one, button push for number two. And the CR stands for control relay. CR stands for control relay. And then CR1 and CR2 turns on the light. And it doesn't turn on unless both are pushed. And this is an OR circuit. It's in chapter 2 of my book. And what is this? This is a circuit where you push this button, it turns on this relay, and there's a feedback that comes around this, and you can lift your finger off this button, and this is closed by that time. So this pushes, closes, this is an alternate path, and what happens? The relay stays stuck on until you push this button over here. When you push this button over here, what happens? It turns it off. You say, why is that important? Well, because anytime you have a memory circuit, you say one thing sets the circuit and another thing turns it off. So when you get on an elevator and you push a button, you don't want to have to hold your finger on that button. That makes good sense. You do not want to have to hold your finger on that button until you get to the second floor or the third floor, whatever. Nobody wants to do that, right? So you want to push a button and it sets a memory. So that's how it's done. So let's look at some of these coils. Let's look at some of these circuits. So this is the one I just showed you with the relay. Here's the one. I'll pass this around with the open thing. This is the one without it. And this is a 12. This is a 9 volt. This is a 12-volt coil, but it works with 9 volts. You can actually, you touch these terminals, you can actually feel it changing state. On that, this one, you can actually see it changing state. You can actually see the contacts with it. You can just see it. So the coil is the 2 on the end, and the other one's on the other end. So you can take that, try it, see if you can get it to work, and actually see the contacts move. And then we've got some more. Now they're based on voltage. I'm going to show you the biggest one here. This is the biggest one I've got. This is a machine tool relay like you'd find in a factory, right there. Up until the 1970s, this was what was running all the logic in most factories. This thing right here. This basically was the reason why programs were invented, because every time they had a changeover in the automotive, they would have to rewire all these in the control panel. It's a very big job, and that's why every time they had a model change, they would basically go through a lot of very difficult, very difficult times. So here's a physical relay that you can try and plug it in if you want to. I'll pass it around. I'd rather you didn't hold this. Well, I'd rather you set it like that, and then don't touch anything, and plug it in. So don't touch the relay. I'll just touch the relay and plug it in. And more. We have more. We have a lot of different ones. These are some different ones. These are the same thing, more of the same, more of that one right there. And I'll pass one around that is taken apart. This is the one that's got a coil. Is there one of those this, that was the one I was coming from? No, this is the one, this is one like those, but it's this one. This is coiled out of one of those. Okay. Now this is a motor starter. It works the same way. It's got contacts in it, just like, but it's rated, the contacts are rated to a motor starter. This is another relay. Some of these are AC relays. These are 24-volt relays. These are 24 volts. These are the ones you're going to use. This is the type you're going to use in your projects. Right there, right there. They're more of the 24 volts. Anyway, that's my story, and I'm sticking to it. And those are some different relays that you can see. Now I'm going to show you the circuit that you're going to be building. I think I've got pretty much the whole circuit built up, but I want to show it to you. So we're going to get this thing in. Now, in this chapter, so this is my my suggestions for this thing. So this is all just handwritten. So I really don't tell you everything here. I give you some of the parts and pieces, but I don't give you every little detail. You have to figure it out for yourself to an extent. But there's a limit switch that trips either high or low when you go to the right and when you go to the left. So basically, this is a limit switch that when it turns on, when it goes to that position, you want it to turn on, and that would be when you go to the right side. This would be when you go to the left side. And you have to determine which is right and which is left. And this is a circuit that after you go to that position, this is a time delay and that is a capacitor. So most of these are contacts. That's a contact, that is a capacitor, and that's a resistor, and this is a transistor, and we'll talk about that a little bit more. But when this transistor, the value of it decays down to 0.7 volts or less, this switches, and then this relay turns state. So this is when you hit the end limit one way or the other, and then this is a time delay after that, an RC time delay, that allows you to then go to the other position. So what you're supposed to do is you're supposed to move okay, so here's your layout. Here's your linear actuator, and it can be either out or it can be back like this, okay? So when it's all the way out, there's a limit switch here that it hits, and when it hits that limit switch, it's supposed to time delay a little bit. So when it hits the limit switch, there's a time delay. And then it's supposed to reverse and go the other way. When it gets back to this one, it hits another limit switch. There's a little time delay. Then it's supposed to turn around and go back that way. Okay. So you're supposed to build this just with relays and that time delay circuit. What that time delay circuit does is this. You have an RC time delay, and it does down like this. And when it gets to 0.7 volts, the transistor switches state, and then it goes the other way. Okay, so this time delay is from here to here, and that's your RC, R times C. So you get your time delay based on the R that you pick and the C that you pick, and you have to pick those. I don't pick them, you pick them. So you need to get something that's about 2 seconds, enough to see that it's a time delay. Now, honestly, you can cheat. And as soon as it gets to this end, it hits the limit switch, starts the other way. I don't want to see that. I want to see an actual time delay. Count a couple seconds, and then start back the other way. That makes it a lot more difficult, because then you have to build that little circuit, the little time delay circuit. Okay? Yes, you can have it immediately switch and go the other way with one relay. This way you have to use 7 relays, and there's that little time delay circuit as well. So you have to build all that in. And you have to design this. I'm not giving you values of R and C. I'm giving you some suggestions, some ways of doing it, but I'm not telling you exactly every little detail, because you have to figure out whether this is opening or closing, whether this one's opening or closing, and how that fits your circuit. So that's up to you. Okay? And you'll get 2 limit switches, and you'll have to solder them. You have to mount them and solder them. Oh, the fun. And then you have to build a circuit with the relays that have been passed around, the little 24-volt relays. Any questions? So get in your mind what's going on, what's actually happening. A little bit of the why we do what we do and why we're doing this. Now, why are we doing this? Make your life miserable, yeah, right. No, because after you've been doing all this other stuff and you see kind of how things work a little bit with AC circuits, and we talk about them in detail a lot, because it helps you to understand phase shift and all that kind of stuff, and why you need to understand that there is a phase shift and you have to compensate for that for power. We kind of don't do too much more with AC, other than we just say it's there. But with this circuit, we're actually using 24-volt DC, but it's used to do something very beneficial, which is control of some devices. And we use this RC time constant to give us a time delay. So we build a timer out of parts and pieces that you know something about. And we take a transistor, which you don't know very much about, but you just have to accept the fact that when it gets down to 0.7 volts, it switches state. It flips from one state to the other. Okay? It conducts until it gets to 0.7 volts, and at 0.7 volts, it stops conducting and it becomes, it turns off. All right? So you have to figure that out, how to turn that, when that turns off, what does that do to that relay that's up above it? Any questions? Any comments? So that's coming, and I've got to get the parts and pieces together for you. But very quickly, once we get through one more lab, we'll start doing this. Okay. All right. So I think we were at the end of chapter 7. We were not quite done with chapter 7, if I remember right. Did I remember right? Where are we at? Somebody tell me. 729. All right, so let's work on 729. All right. Okay. Let's do 729. That's where I thought we were. So let's do that one because that's the one that I'd like you to be able to do. All right. And we'll do one more lab. I think 8 will be the last one, and then we'll start our project. All right, so this is a project type problem, and so for 729, we have 4 loads. We have a supply, that's an AC supply, and then we have 4 loads. This could be this could just as easily be a 3-phase. It's a single-phase load, but we could have a 3-phase load just as easily, and this could be a 3-phase problem just as easily as a single-phase problem. Okay. So one is a 1.2 kilowatt resistive load, 1.2 kilowatt resistive load. So there is no there is no Q power at all. This is a 400 watt resistive load. This is a 0.5 horsepower motor. And another one that is a 1 horsepower and 1 horsepower. Okay, so let's figure out the wattage from number 3 and number 4. So these are pretty straightforward. These give me power in the X direction only. They do not give me power in the Y direction. So I've got 1.2 kilowatts and I have 400 watts. Now I'm going to be doing vectors here. So let's just look at this. And now the wattage from 3 is equal to 373 watts. That is half of a horsepower. So that is equal to 0.5 horsepower. And then the efficiency is 0.8. Now let's see, 0.8 efficient. So this is, so we have to actually use according to him, 373 divided by 0.8 gives me my wattage, my P out is equal to 466.25. Okay. Now he gives us a power factor number of that, 0.7 power factor. Okay. So 0.7 is equal to the cosine minus 1 of theta, and that's the angle of this motor's power factor. It's a very inefficient motor. So this theta right here is 0.7, or excuse me, it's the cosine, the inverse cosine of that, which is what is that theta? Theta is equal to, our cosine of 0.7 is 45.57 degrees. So my theta right here is 45 degrees. This is a fairly steep device. So 45 degrees, 45.57 degrees. All right. So what is my Q? What is my imaginary power for that? Okay, if this side is 466.25, what is this side right here if, this is all trigonometry, right? This is all this is. What would be this side right here? Well, you can find this piece right here and then take the sine of it, and that would be what? How do you find this side if this is 466.25 and an angle 45.57? How do you do that? Hmm? You can take the tangent of it. Very good. So you take the ratio, which is the ratio of what? Sine over cosine? Right? So what would be, okay, so you would say 45.57, excuse me, arctangent equal to what? 0.88. So what is tangent sine over cosine? Opposite over adjacent. So it's a, so it's 80, it's 88 point. Honestly, I have forgotten. So somebody needs to help me here. All right. So how would you find this if you got this and you got the angle? The one I know is to be able to do is to find this and then find the sine of that, and that would be one way of doing it. But again, arctangent is opposite over the adjacent. So okay, so if you want to find this one, you say 466.25. 45.57. Okay, let's try that. Okay, so tangent, okay, let's try that and see what we get. 46, I got the answer, by the way, so we don't have to worry. Times tangent, 45.57. Okay, equals 475, that's right. Okay, that's right. So that gives me 475.62. So now we've got, this one has an X and a Y. The X is 466.25. The Y is 475.62. All right? The fourth one, wattage of the fourth one. is what? It's 1 horsepower, which is 746 or 745.7. It doesn't really matter. And P out is equal to 746 divided by 0.85, which is equal to what? 877.6. So with the fourth one, we have an X of 877.6. And what is our power factor? 0.8 power factor. So what is the angle? What is theta? Ashley.
36 point, yeah, 36.9.
Huh?
36.9 degrees.
36.9 or 36.87 degrees. Everybody agree with that? So what is our Q or our Y direction? What is our imaginary power for that one? 877.6 tangent 36.9 is equal to what? 658.2. So with this one, we have a Y direction of 658.2. Now what do we do? We put all these together. We've got 1.2 kilowatt, 400 watts, 1.2 kilowatts, 400 watts. We have 466.25 and then also 877.6 watts. We add those all together. Then we take these two up this way. We've got 475 and we've got 658. So what's our final answer? What's our theta? Here's our X, here's our Y. What did they ask? That's what the apparent power, the source current, the real power, and the reactive power. So they want to know all these things. So let's just look and see what all they ask. So here's all of our power. What I did was, at this point in time, I divided this by 240, each of these numbers by 240, all right? So what I actually did was, instead of doing it with power, I did it with current. So the current is 5, 1.67, 2.77, and 4.57. And the imaginary power, the imaginary current is 1.98 and 2.74. And that gives me a theta here of what? 21 degrees. Okay, so be able to work a problem like this, all right? This is real world. You have to be able to do this kind of stuff. to be able to, you're out on a farm and you want to know what my total load will be, what my circuit breaker will have to be in order to power these four things out on my back 40, okay? So, I'm milking some cows, I've got a chicken house, I've got a pump system, I've got a thing that heats my garage so I can work in it. And what do you do with all that stuff? You look it all up and you add them all up, and then you come up with a power factor, and you also come up with a total circuit. That's how you do it. Any question about that one? Any comments on that? So I have about 20 minutes, 30 minutes left, and I don't want to overdo chapter 8 and I don't want to underdo chapter 8, okay? Chapter 8 is a chapter that we could explain in 2 minutes and be done with it. And on the other hand, we could spend 2 days in lecturing on it. And, it might mean a little bit more, but on the other hand, it's not a chapter that I've taught this course a lot. And some people get into this chapter and they like it and all that kind of stuff, but most of the time it's kind of like, let's keep moving. Let's just keep moving on because we understand the basic concept, but it isn't a big deal. All right. Kind of like transformers are easy. This is just, okay, we got it. Let's move on. But you need to know that it is a chapter that people consider at least have some importance. Why? Because a basic circuit in radios is derived from this chapter. And that's basically when you have a circuit like this and X sub C and X sub L exactly and opposite counteract each other. In other words, the irresistible force and the immovable object come together and they exactly block each other. What do you have? You just have V over R is my I, because this one cancels this one, all right? And if you lower this one and you don't have very much R, what happens? You get a big current. You get a big current. And that's what basically is happening here. So this is the one, and this is my X sub L, this is my X sub C, and as I bring my frequency higher or lower, one goes high and one goes low. When they go high, we go low, right? Or we go low. What is it? When they go low, we go high. Well, this is one and this is the other. So again, however you want to call it, that's what that is. That's the point of they meet and they exactly cancel each other out. Now, what happens with this is kind of interesting, because if you have a little R, this circuit goes way high, okay? Current goes way up, which is kind of what you'd expect. If you cancel out the R, if you cancel out and have a little R and a constant V, anytime you have a little number in the denominator and you have a constant in the numerator, what happens to the result? It goes high. And that's exactly what you'd hope. Okay? So in that situation, if you can get that, you have what we call a high Q. Q stands for quality. And if you do that, you can basically say we have a high quality or a high Q circuit, which is why we can say in certain circumstances that we can actually take a frequency and pick a Q or pick an L and pick a C and pick off one frequency at which it goes high and at other frequencies it goes low. Now, why would this be important? Well, in this room are all kinds of radio frequencies, okay? And if you want to pick one of them out to exclude all others, you do something like this. That's exactly what they do. They pick a frequency, they pick a L and they pick a C, and then they put them together so that they cancel each other out, and that's where you get channel 13, or that's where you get channel 14, or 11. Where I grew up is channel 14. Right here it's channel 13, channel 11, channel 24, channel 36. You get the picture? That's exactly how it's done. Anyway, I think it's kind of neat. And the better your reception, the higher the Q, right? The higher the Q, the better your reception, higher the quality. So that's how you build that. I'm not a radio guy, and I never will be. I built a radio when I was in high school. That's what convinced me to be. That's not what convinced me to be an electrical engineer. I don't know what convinced me to be an electrical engineer, but that's what I was. Anyway, but I'm never going to be uh, like this. This does not get me excited or anything like that. About no, it's not. This is a low Q. All right. So this is a good one. This is a bad one. So if you design a circuit and this is what you get static. You don't get a good circuit. You just get basically static. Now, how did they determine what they call the bandwidth? There's a bandwidth associated with this. This would be a large bandwidth and a narrow bandwidth. How did they determine that? Well, they take the peak value and they go to 0.707 times the peak value, or it's called the half power point. So you go down this slope till you get to 0.707 times the peak. You go down this slope till you get 0.707 times the peak, and they measure the difference between the two frequencies, and that's your bandwidth. So the bandwidth is the high minus the low. It's the two. It's the separation of the two. So high Q is with respect to the frequency divided by the bandwidth. That's the definition of Q. Q of the circuit. It's the frequency divided by the bandwidth. Higher the number, higher the Q, the lower the bandwidth. All right, so you measure from the peak down to 0.707 times the peak on the left, the peak down 0.707 on the right, take the difference between the two, there's your bandwidth, which is commonly referred to as it's got another. See, these equations I really very rarely I've never. This one you can use. This is good. This is a good one. But some of these are very rarely, if ever, used. And again, I don't want you to memorize these because they are not of no use. They're really, you don't remember them. Okay? So the Q of a series circuit is equal to this. Okay? 1 over R times the square root of L over C. Now that one we probably will use a little bit. I'm not sure how many problems we'll do, if we'll do any. I really don't remember how many problems we do in this chapter, but I'm trying to give you just the overview of this chapter and tell you that it is, if you get the idea of a high quality is a narrow bandwidth, you're in. That's about it. Very rare. There are very few people doing this kind of work, and I don't think. How about this? I know of no one in EET for the 40 years that I've taught that actually have gone into design of radios. Okay? So if you're going to say, well, I'm going to design radios, I think you've missed your boat by about 60 or 70 years. Okay? Now, if that's what you want to do, it's okay. It might be a good hobby, but this ground's already been plowed about 10 times. So you don't need to go over it again. But on the other hand, you need to know that a high Q is a high quality. High Q is to be desired in picking off a good frequency or picking off a frequency in a radio or a TV. And again, I don't know the circuitry inside a TV anymore. I never did. There were stories of guys that built their own TV. There was a guy that was older than me, and he built his own TV. While he was in college, he built it from scratch, and he built it from components that he just, built, and he did it together, put it together. He got hired by Motorola, and he made millions of dollars. He went out to, Phoenix, Arizona, and he worked for Motorola, and basically he became one of their chief engineers. Like somebody from my hometown or whatever, somebody from close to where I live. I never did that. And some of you might say, why didn't you? Because you could have built radios. Okay. I kind of fell into liking to do automation in factories. And that's what I teach. I teach basically that stuff. I also teach this stuff kind of to help you, maybe help you, I don't know. But I'm telling you that, Paul, you need to know about Q and high Q and all that kind of stuff. That's about it. I don't know. I'm being cynical right now, but sorry. Okay, let me see. And this chapter is pretty much just use a couple formulas, and let me see what I assigned, because I don't remember right off what I assigned in this chapter. But it's not much, because I don't really expect a lot out of this chapter. 19 and 21, yeah, 19 and 21. Let's see what 19 and 21 look like, because I don't think I have them worked in my book. Now, maybe I do, but I don't remember them being worked. 8, 19, and 21. Let me see if I got them in here. I don't. It's not that I can't work them. These problems are very straightforward because what are they? They're just using that formula that we just did. That's all they are. And I hate to be so pessimistic about it, but once you got the idea that it's where x sub c and x sub l exactly cancel each other out, end of story. That's about it. And that really is, now that you've done all this stuff, to be able to say that and be able to say, oh yeah, I can see how that works. Next. Next. Anyway, I don't think I worked them out. 19 and 21, let's just see. Nope, I don't think I have them worked. Sorry about that. Example 8.6 is the only problem that I worked. So let's just go back and look at 8.6. Go to 8.6 and see what that one's about. Okay, let's do this 8.6 because this is not that I'm going to give you this one on a test, but an inductor has an impedance. Now, this would be just a straight inductor has an impedance of 3 plus J150. Okay. Determine a parallel resistance and reactance that produces the same value. Okay? So I want to convert this to something that is like this. So 3 plus J150 is equal to what? This would be R, and this would be JX. So 3 plus J150 is equal to R times JX over R plus JX. That's my parallel rule. All right? Now, what are the two parts? The real part must equal this. The imaginary part must equal that. Now, this is something where you have to play the game. So you have to do what? 3 plus J150 times R plus JX is equal to R, or J times RX, right? You have to multiply this all out. So he does this 3R plus J150R. So this is this one times this one plus 3JX minus 150X is equal to JRX. Now the real part must equal the real part, and the imaginary part must equal the imaginary part. Okay? So the 3R must equal 150X. Everybody see that? The real part is that and that part right there. And the 150R plus the 3X is equal to RX. That's the other part. How do you find from these two equations? How do you find how do you find R and how do you find R and X?
Take the first one and you divide it by 3. You
Yeah.
take R by itself, and then you split the 2
Very good.
into the second equation.
You get the R's in terms of X's. So R is equal to 50X. Everybody see that? Now 150 times 50 times X plus 3X is equal to 50X. Okay, so R is equal to, okay. X squared, right? Cancel, cancel, cancel. X is equal to 150 times 50 plus 3, or 7503. What's 150 times 50? $7,500. So it's 75 is equal to 7503 divided by 50, or it's equal to what? 7503 divided by 50 is equal to 150.06. And that gives me my value for my X, and then my R is equal to whatever it is. It's divided by 50, and that gives me my value of R. So it's basically the same, except just a little bit of difference, but not much. Instead of 150, it's 150.06. And instead of 3, it is 3 point. It's a little different, but not by much. Does everybody see how that's done? You have to basically go through this razzmatazz in order to get it, but you can do it. All right, now let's go down to 19 and 21. These are more of the, okay, I think the reason I didn't do any more than this with this one, these two, is because, why, Ed? Because they just follow the formulas. So 19 and 21. All right, so 19, you have a 15-volt circuit. And 33 nanofarads capacitor. And a 41 microhenry inductor. Our coil, which we don't even know what it is. And 3.2 ohms. Now, what they want is resonant frequency, Q, and the bandwidth. Now, all these are, that's why I don't do much for this chapter. Okay, so all that this is go back and find a series or a parallel. There's a set of formulas for the parallel circuits. So these are canned formulas. This is not anything that you're going to have to do anything with other than you find that where this says parallel back here. So you go back in the chapter, find the formulas for the parallel, plug them in, and you got it. Okay? So let's just look at the parallel circuit. Parallel resonance, okay? Series of parallel. Okay, so that's all that is. Now let's go back here and find, okay, Q. Okay, here's my formulas. Q parallel. Okay. Square root of C over L. So they're just canned formulas. Oh, I'm sorry. Yeah, this is it. This is all it is. Okay, so if there is no R in parallel here, the R total is the parallel of the two, which is basically 3.2 ohms. All right, so R total is that, X sub L is that. But let's go down here and see what the Q is equal to this, which is R total is 3.2 ohms times square root of C over L. The resonant frequency is 1 over 2 pi squared of LC. That's my resonant frequency. And my bandwidth is what? Is F0 over, okay, so my bandwidth is F0 over Q of the circuit. Q of the circuit is Q of the circuit is the Q of the parallel. Yeah, this Q right here is the one you use right down here, and that's all this is. So the bandwidth is the F0 over the Q, and that's it. So it's basically canned formulas, that's all it is. And I'm not going to belabor it. That's all it is. Now let's go down and do 221 and see what that one is. Okay. So let's go back and do the number 8, because I should do this for you. All right. So that you have a little bit of an, you know. Okay, here's my example 8.4. Okay, in this case, is equal to, this is example 8.4. So this is using example 8.4. F0, which is my resonant frequency, is equal to 1 over 2 pi square root of LC. Q, the coil, is X sub L Yeah, so the Q of the Q is the Q of the coil because there is no parallel resistance. So the Q of the coil is the same as this one. So here's my formula for F0, X sub L. Then you get X sub L from that. X sub L is 2 pi times F times L. Q coil is equal to X sub L over 3.2 ohms. And my bandwidth then is bandwidth is equal to F sub 0 or FR over Q. And that's it. That's all you do. Again, I'm not a fan of these problems because they're just little, probably not have anything in them. If I do anything on this, it'll be a canned problem like that one, and that's all it'll be. And I'll give you that as a preliminary to any test. How's that? This is not stuff that you need to memorize or need to learn, other than the fact that you need to know what Q is, high quality. When they talk about Q, it's high quality. Okay, the circuit here, this one does have see, this one does have the parallel resistance in, so this one does use that resistance in there as well. So this one is a little different than 19 in that my resistance all of a sudden is jacked up. And this will have a lower Q because you have the 4.7K resistor in parallel with this resistor, which makes it go higher. Anyway, that's all it is. 19 and 21 are right out of the book exampled questions, and I probably will never ask you anything about them. If I do, I'll prepare you very well. I promise you it'll be, here's the equations, and be done with it. That's why I don't like this chapter. How's that? Okay, enough. Any questions anybody's got? Chapter 9 is not like Chapter 8. Chapter 9, we will camp on a little bit and we will work on it. And then Chapter 10 is a good chapter, but we don't use Chapter 10 as is. We use it from another book. So we talk about it, but not from this book. I do not like this book for Chapter 10. But we'll learn how to do Bode plots. And that's it. And then we'll get on to our project. And once we get into our project, I'll talk about it extensively, and then we'll get on to other stuff. We'll go into the electronics book and talk about it some, and we'll talk about program controllers some. So we've got a combination of things we need to work on in order for you to get your project done, and also for you to get an example to get started into the electronics part of this curriculum. Anyway.